Okay, guys, we're going to try to do this by recording, so here we go. We're going to start chapter 14. We're going to continue our discussion about extrema. Remember, in chapter 13, we talked about relative maximums and minimums. Remember, that's when the first derivative changes from positive to negative or negative to positive. We can find all the places on a graph where the graph goes up and then goes down, or goes down and then goes up, right? Relative extrema. But we're going to add to that discussion today and talk about absolute extrema. Which one of those maximums is the absolute maximum value, or which one of the minimums is the absolute minimum value, where the largest possible value of a function is called the absolute maximum, and the smallest possible value is called the absolute minimum. Sometimes we don't want to find just the relative maximums or minimums, we want to find the highest or the lowest value. Okay, so looking at this graph right here, we have a couple of different places where our derivative changes from positive to negative or negative to positive. Right here at x sub 1, we have a relative maximum. At x sub 2, we have a relative minimum. And at x sub 3, we have a relative maximum. But if you take a look back and see which one of those is the highest, x sub 1 is not only a relative maximum, he's also the absolute maximum value on this function. He is the highest value that this function ever hits. So we could call him a relative maximum, but more specifically, we can also call him an absolute maximum. Where x sub 2 is a relative minimum, but there's other places on the function where it goes lower than that one, so we wouldn't call him an absolute minimum. Same idea with x sub 3. He's a relative maximum, but he's not the highest value, so we would just call him a relative max, not an absolute max. Actually, on this particular function, because we have arrows symbolizing that that function is going to continue to go down and out, there would not be an absolute minimum because it just keeps going down, 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 down. There is only an absolute maximum on this picture. Okay, so let's look at a few other pictures. This extreme value theorem says that if you have a closed interval, you have endpoints on both sides, it says that your function has to have then both an absolute maximum and an absolute minimum. So take a look at these three different pictures. On the first one, you can see that we have a highest point. It goes down to the lowest point and then ends here. So this point right here would be our absolute maximum, and this point right here would be our absolute minimum. On the middle graph, because it's a straight line that kind of goes diagonal, this would be our absolute maximum, and this point over here would be our absolute minimum. On our third graph, we have some relative maximums, we have relative minimums, we have relative maximums. This one, because it is the highest point on my graph, is also an absolute maximum, and this one also happens to be an absolute minimum, where this x sub 2 would just be still a relative maximum. Comparing all three of those graphs, you can notice that on some of them, my absolute minimums or maximums happen to be at those relative extrema. But on some of them, my absolute maximums or minimums actually end up being my endpoints of my graph. Okay, so that's kind of what we're going to do in order to figure out if we have an absolute max, excuse me, or an absolute min. We're going to figure out where our relative extrema are, where do we have those ups and downs, but then who could be higher or lower than those relative extrema? Well, if my endpoint goes up higher than my maximums, well then that's my absolute maximum. If my endpoint goes lower than my minimums, then that's my absolute minimum. So again, absolute maximums and minimums could happen at any of these places or at my endpoints. Okay, so there are a couple different steps that we're going to follow in order to find absolute extrema. The first thing we're going to do is we're going to find the derivative. We're going to figure out when our function goes up and down, increases, decreases, where that derivative kind of changes, right? We're going to find our critical numbers. That's where our derivative equals 0 or does not exist. We're going to take those numbers then, our critical numbers, and we're going to evaluate those in our original function, because if we can figure out where it's at and then compare them, then we can figure out where the highest value is versus where the lowest value is. The next thing we're going to do, remember, because who could be higher than those critical numbers, those relative extrema, is we're going to take our endpoints and evaluate them in our original function. Okay, so we're going to find our critical numbers. We're going to take those critical numbers and plug them into the original. We're also going to take our endpoints and plug them into our original, and then see where the highest value is for our absolute maximum and where our lowest value is for our absolute minimum. Let me show you an example. All right, and we're going to go a little bit faster, so you might need to pause the video because I have all of my stuff pre-written. So like I always say, don't just be a copy machine. When I ask you to try it, I want you to pause the video, try it, and then play the video again and make sure that you're on the same page as me. But I'm going to go a little bit quicker just so that the video is not so long, okay? So here we go. Example number 1 asks us to find the absolute extrema of the function on the interval from -1 to 8. So I have this graph, whatever it looks like, and I want to look at it from -1 to 8, and I want to find where the highest value is and where the lowest value is. Remember that step number 1 is to find those critical numbers. But before we can find those critical numbers, we've got to find the derivative. So pause your video, find me the derivative, make sure you practiced all that, and make sure you have the same answer as I do. Okay, so I got a derivative of 8/3 x to the 5/3 minus 16 times 2/3 times x to the -1/3. Remember, bringing your exponent forward and then subtracting 1 from your exponent. From here, I'm going to simplify a little bit. I'm going to take these fractions here, put them together. I'm going to make this exponent positive, remember, by dropping it down. So again, pause the video, try it, and see if you get the same answer as I do. Okay, so on this first term, I have an 8 on the top, I have an x to the 5/3 on the bottom, and then I have my 3 in my denominator. On my second term, I have a 32 on top, I have a 3 on the bottom, and then I have that x to the 1/3 on the bottom to make it positive. From there, what I want to do is try to get a common denominator so I can get one fraction. So if you look at both denominators, they both have 3's, but the first term needs an x to the 1/3. So I'm going to put an x to the 1/3 on top and on bottom. Now that I have common denominators, you should be able to combine the numerators and then combine the denominators. So on the top, you should have an 8x squared minus 32. The x squared came from these two terms. When you multiply, remember you add the exponent, so 5/3 plus 1/3 is 6/3. That's an x squared, right? My common denominator is still that 3x to the 1/3. So this is my derivative. My next step is to find my critical numbers. Remember, that's where my derivative equals 0 or does not exist, right? I want to find all those places where I could possibly have highs and lows, where the derivative equals 0, or maybe where the derivative doesn't exist. So let's find those critical numbers by, again, figuring out where the derivative equals 0, that's the top equal to 0, and where the derivative maybe doesn't exist, that's the bottom equal to 0. So finding my critical numbers, I'm setting the top equal to 0 and the bottom equal to 0. I'd like you to pause the video. I'd like you to solve both of these equations and find me your critical numbers, please. Okay, for the top, I ended up getting x equals plus or minus 2. Remember that anytime you square root, you should be adding a plus or minus. So I get critical numbers at positive and -2. I also got critical numbers at x equals 0. So I have 3 places where my derivative equals 0 or where it doesn't exist. Maybe sharp turns, maybe smooth curves. We're not really sure what they look like yet or where they are. And our goal is to figure out which one of those is the highest or the lowest. Back in chapter 13, remember we did our sign chart and we kind of figured out where our derivative was positive or negative. That kind of told us the shape of our graph, but it didn't really tell me how high these things were. And so because we're more curious today about how high they are, what we're going to do now is we're going to take all of these critical numbers and we're going to plug them into our original. Because if I plug it into my original, that tells me exactly where I'm at, and so then I can kind of compare which one is the highest and lowest. So I'm not really concerned with increasing and decreasing. I'm more concerned right now with who's the highest and the lowest, where it's at in the original. So my third step is to take those critical numbers and plug them into my original. So I'm going to take the -2, I'm going to take the 0, and I'm going to take the +2 and plug it into my original. You noticed here that I crossed off -2. Why do you think that is? Well, if you remember, in our function or our problem, we were just focused on the interval from -1 to 8. So -2 is outside of that window, so I don't really care about -2 on this particular problem. So that's why I crossed him off. So right now, all I want to know is, when x is 0, what is my y value? How high or low am I? And when x is 2, what's my y value? How high or low am I? So I'm going to take those two values and I'm going to plug them into the original function. But remember, who could be higher or lower than those relative extrema? Remember the endpoints, right? And so what I also want to do is I want to evaluate -1 in my original to see how high or low he is, and 8 in our original to see how high or low he is. Because I want to figure out which one of these points is the highest or the lowest. So now I need you to take -1, I need you to plug it back into the original problem and evaluate where we're at. I need you to do that for 0, 2, and 8. Pause the video, plug it into your calculators, and make sure you get the same numbers I do. Okay, make sure your numbers match mine. When I plugged in -1, I got -15. When I plugged in 0, I got 0. When I plugged in 2, I got -19.05. And when I plugged in 8, I got 192. So out of those values, who would be then the absolute maximum? Well, it looks like here would be my absolute maximum because that's where my highest y value is. And who would be your absolute minimum? Well, it looks like this one would be my absolute minimum value. So I would say that my absolute minimum value is -19.5, and that happens when x is 2. Or my absolute maximum value is 192. That happens when x is 8. Okay? I even gave you a little picture off to the side so you can kind of see what that means in my original function. I have some places where my derivative doesn't exist, that sharp term. I have some relative extrema. If you were to continue your graph, we have another one here at -2, but because we're not focused on that interval, it doesn't show up on this picture. But who could be higher or lower than those endpoints? Or excuse me, those critical numbers. Remember my endpoint, so that's why we had to test those as well to see where we were at. Okay? Again, we found our derivative, we found our critical numbers, we tested those critical numbers and our endpoints into the original. Okay? All right.